start now, or maybe wait for 2 more minutes? Let's start at 4:05 in basically 1 minute. Okay, I think we can start now. So, hello everyone. Welcome to this online seminar on safe reinforcement learning. My name is Alap Shirsagar, and I'm a postdoctoral researcher at TU Darmstadt. I am one of the co-organizers of this seminar, along with Shangding Gu, Yali Du, Yu Hao Ding, and Josifowski. So today our speaker is Puzzle Liu. He's a 4th-year PhD student in the Department of Computer Science at TU Darmstadt. Under the guidance of Professor Jan Peters, Puzzle's research has focused on the intersection of robotics and machine learning. Prior to his PhD, Puzzle obtained his bachelor's degree from Tongji University and his master's degree from TU Berlin. His current research focuses on developing safe and reliable learning robots in dynamic environments. Welcome, Puzzle. We are looking forward to your talk.
Okay, thanks, Alap, for the kind introduction. And so what I'm trying to talk about today would be the safe and reliable robot reinforcement learning in dynamic environment. So I will try to focus on the safe reinforcement learning from a robotics perspective. As many of you have already looked into the reinforcement learning, that basically is Atari games and Go would definitely be one of the most impressive work in the past, right? And people are also trying to work more and more on to deploy the reinforcement learning to robotics platforms such as this dexterous manipulation, and also doing the locomotions with the work from ETH. So one of the questions that comes to my mind is, like, when we are trying to deploy reinforcement learning, how for example, in the human-involved environment, how we can really ensure that the reinforcement learning will not harm the environment, harm itself, and not harm the humans. So the key question is that what I'm asking myself is, like, how to build safe and reliable reinforcement learning algorithms for robotic systems. There are actually several challenges that I consider to be important for the safe robot reinforcement learning. So first of all, you need to have the physical interactions with a real robot, so you cannot really afford pretty heavy damage. And there will be also a high cost for repairing the robot, and you are also handling a dynamic environment, which it will be hard to enumerate all of the circumstances in the simulation. And you will also to deal with the disturbances and also the noise that comes from the real world. And also your simulation is always simplified. Maybe you will have some softening of the constraints. So all of these kind of factors makes your simulation does not really match to the real world. And then another part would be also, like, how can we formulate the safety problems? And all these kind of challenges makes the robot reinforcement, safe reinforcement learning, pretty hard problem. So in the typical safe reinforcement learning, like literatures, people are focusing on several different types of safety constraints. So the most typical one that people are using is this cumulative cost. So basically, you are trying to solve the expected cost over some horizons to be smaller than a threshold. And you can write as smaller than equals to 0. For this kind of constraints, you basically do not need an explicit form of the constraints to solve the problem, because everything is based on the expectation. So you are solving with samplings. And you can also have maybe long-term trajectory level constraints. For example, the total energy consumption should be smaller than a threshold. But there will be also some limitations that you don't have proper safety guarantees during the training process or during the exploration process. And you also need to have a really good simulation such that your state transitions matches to the real world. On the second part of constraints that people are working on is this value at risk, or people are sometimes they are also working on with conditional value at risk, that you are trying to ensure that the probability of the constraints violations is smaller than a threshold, or here is the constraint satisfaction is bigger than a certain probability. And this kind of constraints, you will also consider the noises and disturbances, and probably you will get more robust solutions. But also they have some pretty limited assumptions. For example, you don't have sufficient mathematical tool except the Gaussian assumptions, or you do sampling based with when you are working with this conditional value at risk. And it's also always resolving to some conservative policies. The third part of the constraints that people are considering is pure stepwise hard constraints, that at every time step, your constraint should satisfy at every time step, you should meet the constraints requirement. And this one, you can guarantee, if you solve the problem with this type of constraints, you are guaranteed that the safety during the exploration, and you can directly enable learning directly in the real world, but also you probably need a lot of prior knowledge to make to build up this kind of constraint satisfaction. But in my perspective, like as we are working on robotics, which is also some safety critical problem, and also like there are quite some prior studies about like the robot dynamics, kinematics, which we can directly incorporate to work like for safety critical problems. And we believe that this way we will have better safety guarantees. So therefore, we are focusing on the hard constraint setup. And in this kind of setup, we all usually can call them as also safe exploration problem, that you want to maximize the expected cumulative reward while satisfying constraints at every time step. Okay, so the core idea that what we are trying to solve this problem is we are trying to build up a constraint manifold and a corresponding action space, such that if we can control this, all of the control actions can move the state along the tangent space of the constraint manifold, we are ensuring the safety. So basically, as illustrated in this animation, that we construct a blue plane, and all of the states, we are ensuring that it's moving along the tangent space of the constraint manifold. I guess maybe people will be confused, like, okay, what is manifold? Let's maybe dive a bit into the details of this kind of mathematical form. And if you have any questions, just feel free to interrupt me on this kind of technical part. So the first concept that I would like to introduce informally is the embedded manifold. So basically, embedded manifold is actually a set of points which satisfies the constraints that the function equals to 0 or equals to any level sets, for example, 1 here. And M will be a m-dimensional submanifold embedded in Rn if F has a constant rank, which is the constant rank R. And the constant rank basically means that the Jacobian or differential of the function remains a constant rank. That seems to be a bit abstract, and I will give you some examples. For example, like a circle, like a unit circle, that we can define the constraints to be x1 squared plus x2 squared minus 1 equals to 0. And if you see from the Jacobian, that is 2x and 2x1 and 2x2, on the manifold, you can ensure that the Jacobian has always rank 1, and which ensures that a circle is an embedded manifold that is a 1D manifold embedded in R2. Another example is like this kind of manifold, maybe not manifold, but that we define the constraints as x1 squared minus xq quadratic equals to 0. And at this, the Jacobian is also like a 2x1 minus 3x2 cubic. If you consider the 0 point or this origin point, at this point, the Jacobian is not full rank. And instead, actually, this thing is not a manifold, because you will have at point that you don't know which direction that you should move. Okay, since this is a basic concept of the manifold, it always deals with the equality constraints. But what we are handling or what we are discussing in general would be inequality constraints. So we need to introduce a slack variable, and such that we can construct a equality constraint. So as you can see here, that we introduce a mu, which is n-dimensional, with corresponding to the image of the constraint function. And then we have also the we introduce a h function, which each dimension of the h maps a real value to the positive value, such that we ensure this equality holds. And then we can also get the Jacobian that will have two parts right now. That the first part of the Jacobian will be the differential of the constraint function, and the second part will be these slack variable functions. As a simple example that you can see from the most simple constraints, that x, we want to ensure that s is smaller than equals to 0. And we can construct the manifold and calculate the Jacobian. And if you see this Jacobian, it always have a constant rank 1. And as an example, that this white curve is actually the constraint manifold that we have constructed. It's a 1D curve embedded in 2D space. And if you see that all of the points on the curve ensures that the S is smaller than or equals to 0. Okay, I will give you some more examples on the constraint manifold to make this kind of concept more solid. The first one is that we have a two-dimensional case that we want to ensure that the inside the unit circle region. So we have x1 squared plus x2 squared smaller than 1. And we can construct this manifold by introducing this slack variable. We can use, right now we are using the exponential, but you can choose also other type of functions in this case. For example, yeah, we have some functions in the paper which will be a bit complex to introduce here. And if you see that this Jacobian is also have a constant rank, since all of the points that only the points that can be problematic is x1 equals to 0 and x2 equals to 0. But at this point, the exponential of the mu is actually the log of the 1, which is, no, sorry, exponential of mu is actually equals to 1 if we want to maintain the manifold. So this ensures that our Jacobian is also a constant rank. And here the figure illustrates that this blue parabol surface is the constraint manifold that we have constructed. And also all of the point on the surface ensures to stay within this cylinder tape that is have a unit radius, radius of 1. Another example that is in the one-dimensional case that we have two constraints that both on the left and right side. And we can also add the two slack variables here and construct the constraint manifold, which is also three-dimensional, but has two slack variables. And here is actually the manifolds that we can construct it. It's this blue curve that can be obtained by two curved surfaces. And these two curved surfaces is basically determined by this x plus exponential mu1 minus 1 equals to 0, and the minus x plus exponential of mu2 minus 1 equals to 0. And yeah, also you can also see that all of the point on the manifold actually is ensured to stay within these kind of two planes, gray planes that have determined the x1. X should be smaller than between minus 1 and 1. Okay, any questions so far?
I put there's a question from the audience. You can see the
okay. Then seems every people understand this point, and I can keep forwarding. So once we have determined the constraint manifolds, the second part that we would like to move on the tangent space of the manifold. So we need to first know what is a tangent space. The tangent space is actually a linear subspace, which ensures that a linear subspace consistent of this vector v, such that this Jacobian of the constraints times v equals to 0. And we can also, since it's a linear space, we can also determine at the linear space at each point. Sorry, so we can also determine the basis of each of the tangent space by a set of vectors, or in writing the matrix form. So each of the basis is actually stays inside the manifold and spans the whole space. And we can ensure that the Jacobian C times B is equals to 0. And after determining this thing, we can use this kind of basis to determine the state velocity, which is this xc dot. It's composed by the mu dot and the s dot. And we can determine this kind of velocity on the tangent space, which we can also ensure that the velocity of the constraint violations is equals to 0. Basically, this Jacobian C times the basis C times the AC is equal to 0. In this kind of case, we can ensure that we can choose arbitrary A while maintaining that our constraint violations equals to 0. Therefore, we have already constructed our ATACOM controller, which stands for the acting on the tangent space of the constraint manifold. In this controller, we actually have another term added into the state velocity, which is this contraction term. So the propagation term trying to be tangent to the manifold at each of the points, and the contraction term tries to retract all of the points back to the manifold. Here is a toy task that we have looked into at the very beginning, that we have two types of constraints. We have two types of constraints in this kind of in this task. The first one is that we want to maintain this blue dot stays on the circle. And we also want to not blue dot, red dot. Okay, so and we also want to ensure that this red dot stays above this kind of purple line. And as you can see that even at the 0 epoch, the action is randomly chosen to move. It's a one-dimensional action that move along the tangent. And the final, like after training, some training time, we are able to really stay on the manifold and reach into this green point, which is our target. Okay, and also we have also tried to deploy our task into a more robotic scenarios. In this kind of task, we are trying to maintain our end effector stays on the table surface and trying to hit the puck to the opponent's goal. But what we are controlling is the joint velocities. And we also add some other constraints in the joint space, for example, trying to ensure the joint stays within its limit and trying to ensure that the velocity is staying within the velocity limits. And for example, also have another constraints that try to ensure the elbow of the robot doesn't collide with the table. So in total, there will be 20 constraints ineffective at this task. And after like 100 epochs of training or sometimes of training, we are able to explore sufficiently on the table surface and trying to find the decent behavior of the hitting. It's not scoring 100% sure, because this kind of task is pretty challenging because there will be two wrong shapes colliding each other, and the small difference on the position arrow will directly give you completely different behavior. But in this kind of approach, we actually have some limitations. The first type of limitations is that we really need a tracking controller that can track the velocity c dot. And also we assume that all of the states related to constraints should be controllable. But this will be not generally the case. For example, if you have a dynamical moving object that is not your robot, you cannot really control the things. So instead, we are trying to propose something to make some extensions to our original approach that we made some assumptions. The first assumption that we made is that we have a separable state space. Basically, Q is the state space of that is controllable and X is not controllable. Q can be also some joint configurations and the X can be positions of the obstacles, for example. The second assumption that we have made is that we want to use some good assumptions that in robotics research always do this control affect system. So your state have a dynamics that Q dot equals to FQ times GQ times the control input U. Therefore, we have a slightly different construction of the constraint manifold, which considers 3 input in this kind of scenario. And we can also compute the time derivative of the constraint function. And there comes to, in total, 3 terms. The first term, the Jacobian X and Gx, JQ, G mu stands for the partial derivative of the constraints. And then you will have also different velocities for different terms. We can also substitute this Q dot with the alpha system and group all the things together. So we will get in the end this C dot equals to the psi plus JC times U and mu dot. And mu dot is actually the slack variable that is can be freely controlled since we introduce manually by ourselves. So what we have observed the property is that in the previous setup, we have observed that the C dot equals to 0. And this is also the property that we want to have here, that the C tilde dot is equals to 0. So we want to solve this equation, and we will get a general form AutoComp controller. In this kind of controller, actually, there will be one additional term, which is this drifting compensation term. So there will be some drift caused by the system dynamics, or maybe some drift caused by this X dot, which we can use this term to compensate. And this contraction term tries to retract your state back to the manifold. And this term is actually the reinforcement learning agent should deal with that. We can sample arbitrary A and ensuring it is becoming safe. And here is basically some controlling paradigms that regarding this controllers. So your action is your reinforcement learning agent only deal with the tangent space actions. And here we have some experiments that trying to work with this kind of setup. So there will be a blue robot that is a standalone robot that moves blindly to its goal. And we also have trying to use a differential drive, which has this kind of control offense system structure. So we are controlling this white robot to reach the red goals. And if you see from the pure SAC agents that we trained, it cannot really avoid the collisions sufficiently good. On the other hand, if you see that when the AutoComp is combined with the SAC, then we have a predictive behavior about the velocity of the blue robot and trying to avoid the collision successfully. Oops, I think, okay, sorry. So this part would be that we focus majorly on the constraint on designing the safety controllers. But there will be also another pretty challenging task actually is how we can define the constraints. For the simple task like this collision avoidance, we can directly use a point distance to measure, but it will be in general not the case. And also defining these constraints can be task dependent. And you also need a lot of expert knowledge and analysis, which would be very, very heavy. We don't have a clear answer, but in the first attempt that I would like to really focus on the most common safety issues in robotics, that is collision avoidance. But we also want to really focus on some more challenging tasks that, for example, doing the collision avoidance in the human-robot interaction scenarios. In this kind of scenario, that you will have a human have a shared workspace with a robot, so the human will behave dynamically, and you also will want to make the robot to achieve a delicate and reactive manipulation task. So for this collision avoidance, the most typical approach that people will discuss, introduce or talk about is that we would like to ensure the distance between my robot and the obstacles to be bigger than a threshold. Most typical approaches that people are doing is using some primitives to approximate the geometry of the obstacles. For example, using some spheres or cylinders to describe the objects. This one gives you pretty simple computation, and the distance can be globally well defined. But it would be very, very poor to scale to like more complex geometries. For example, if you want to model a shelf which have very, very thin plate, it will be very impractical to model this with spheres. On the other hand, these functional approximations, such as neural network, have more powerful local representations, and they can also handle complex shapes, but it will be poor to have extrapolating abilities. So what we are trying to propose here is actually a sign distance function. We call it the regularized sign distance function that trying to combine the advantage of the both approaches and then neglect the disadvantage. And we also want to have include the articulated objects such as a human or the robot that can be considered when calculating the distance. So this is basically our red SDF structure, that it has a neural network component that gives you powerful local representations and can handle complex shapes. And you will also have a point distance that can be globally well defined. The sigma theta here is actually a mode switching function that is basically a sigmoid with two parameters. One is this alpha theta controls the stiffness of the mode switching, and the rho theta would be the center where the mode switching should take place. And we basically use this kind of network to train distance functions with such kind of network structures. So here are after some training, we have pretty good results, I would say, for different type of geometries. For example, in the table shape, that you will have very thin plates, and also you can see the details on the shelf on this part, which is also reconstructed from the network. And we also consider some articulated objects like the Tiago robot that have a moving arm, and also the human, which have 24 moving joints, if I'm not wrong. And our red SDF also have a pretty good extrapolation ability. Oh, sorry. Okay, as you can see that in our approach, that when you are computing the distance at the far end, it will basically smoothly vary into a sphere, which is in many cases would be a good approximation. But for some other deep network based approach that you will maybe not have an evenly spanned distance, or you probably have some outliers, or the distance is not globally well defined. And here is actually some experiments that we have done before that trying to show, okay, how our distance field it varies at the when as a robot is approaching. So in this task, we are trying to define a safe distance based on the distance between the human and the robot, and trying to visualize, okay, all of the distance field varies from a smooth and a big blob into sufficiently details of the human hand, for example. And then we also have integrated this kind of approach into the safe reinforcement learning. For example, in this case, we have integrated the train distance field of the table and the Tiago robot to achieve goal-reaching task while avoiding collisions with the robot and also with the Tiago robot itself. And surprisingly, that we train all the things in the simulation, but it's like transfers to the real robot without any problems. And if you see that we train to reaching the single goal, but if we put multiple goals on different points, it will also be very easy to reach. And also, we have observed that actually our approach is achieving sufficiently faster learning performance compared to the baselines. This is actually because we are always giving you a safe action space. And so there will be no terminations, or very rare the termination will happen when the constraint is violated. And we will also have a limited exploration space, which actually helps to boost the training process. And in the end, we also have trying to incorporate this kind of task into a human robot scenarios. As you can see here, that in this task, that the human is trying to play with a phone and trying to reach to some objects without really taking care of the robot. This is our initial setup. And if you see from the left point clouds that we have incorporated all of the train distance field into it, and the policy was transferred without any barriers, and it's actually working very well. And we have also compared this approach with typical a linear attractor approach, and it seems that the reinforcement learning agent is really able to get to some local minimum. For example, if you press from the top, the linear attractor approach will try to not avoid just stop at some balancing point. And we also done multiple different experiments with the humans and with different motions and different configurations. Surprisingly, that we don't have any violations during the with the constraints. We don't have any constraints violations or collisions happens during this experiment period. And also, if you see that at the very beginning of the experiment, the human was a bit afraid to do the motion, that they are trying to really do careful, slow motions. But after some experiments, as you can see from this video, that the human is completely not taking care of the robot and do the motions. And this is actually what surprises us, like how human can adapt its behavior based on how reliable the train policy is. Okay, that's I would also like to make a bit off-topic part, and maybe not completely off-topic, that on some advertisement that we are trying to organize air hockey challenge this year, which we are trying to have design. The challenge is divided into 2 stages. At the first stage, that we will have 3 different individual tasks, and we will also deploy some. You need to deploy some safe learning methods, which ensures that the robot doesn't collide with the table, doesn't violate the constraints that we have on the individual task. And afterwards, on the second tournament stage, we will also try to make the robot to have a full game that basically each team will compete with each others. And this kind of things, I think it will be a good fit for the safe reinforcement learning approaches that if you want to deploy or trying to explore. Since we also have joint space constraints, task space constraints, and we also have different real-world factors that involved in the simulation. Okay, as a wrap of the talk, I have introduced 3 different 3 approaches. That the first one is ATACOM, trying to ensure the safe exploration of the tangent space of the constraint manifold. We have also extended the method to in the dynamic environment, and also consider the robot dynamics with a control system, and to construct the to tackle with complex problems, we have also developed some distance fields that ensures you to do safe exploration with by constructing complex constraints. Okay, that will be the talk for me today, and yeah, happy to take any questions.
Thanks,
Okay,
Susan.
great.
I think there's a question in the Q&A box. Can you see it?
Yes. Hey, but can you say the question and answer?
Let me quickly go to the
Yeah.
Q&A because I didn't actually find them.
Okay, maybe read for you.
Yes,
if one wishes to use safe reinforcement learning in the context of safety of machinery, for example, robots, one needs to consider what will be possibility of single technical failures. Can thus be formulated as hard constraints. This may be speed limits, position limits. But there is also the layer below in which diagnostic functions detect a failure in the control system, which leads to trigger a transition to a safe state. How to combine this with the safe reinforcement learning is not clear to me so far. Is it a relevant question for today? Okay.
Okay, wow, that's a pretty long question that I have to.
I will put it on the chat. You can
Because
see.
I would like to also, yes, thanks, because I cannot really see the Q&A. If I finish this session, yeah, actually, that's actually a good question, because this is also what we are thinking about, like during the constraints definitions. Like we don't have a clear or unique definition of about the constraints, right? Because in general, for different tasks, you will have different constraints. But at least in our perspective, the first step that how we should tackle the constraints is the most intermediate level that. you should ensure that every time step your constraint should be satisfied. And then you can probably also incorporate this kind of safe exploration method with the more typical safe reinforcement learning approach, and trying to deal with the constraints in the trajectory level, or deal with expected cost and stuff like that. And yeah, but that will be definitely future directions that I would like to look into, because I don't have a clear answer, like what would be the best constraints definition, but yeah, working with intermediate constraints would be the first step. And but there's also a layer below in which the function detects in the control. Yes. I mean, definitely, like you can also do the diagnosis as a part. Second part of the question is like they are asking there will be a diagnostic function detect the failure in the control system that can be also incorporated. Yes, I agree that for example, you can also have some safety guarantees or stability guarantees in the very low level to the tracking controllers, and you can also have some robust controller trying to deal with how to say disturbances and noises. And this level is actually also important, because in our case, we also need to really design the controller properly that is able to track our desired behaviors in a sense. But in this case, I think it would be more on the decision level that we are trying to look, okay, instead of looking into the very low level on the talk level or on the command on the talk level of the controller, we are looking into more decision, like how you should go and where you should go. And this part is actually also important in the reinforcement learning.
Okay, I have a question about the Atacom method. So there you mentioned that you have these slack variables, and
Yes.
You tried different functions for them. Can you describe how did you choose the functions, or are there any conditions?
Okay, so let me quickly jump back to the slides, because actually this one is one important factor, but it would be too technical that I didn't really want to include. So one of the important things is that we want to choose the slack variable that ensures the Jacobian to be constant rank. That's why in general we choose this kind of exponential variable that it will never goes to zero in general, unless your mu goes to infinity. In the past, at the original paper, that we also choose the cubic or quadratic function like s plus mu squared to be zero, but this one is actually converging to the 0 point, which is not desirable, because this point can be problematic that you will not really, and it will also cause ambiguity issues, because if you think about the quadratic one, it will be a parabola. And this parabola, you will have actually, for each individual state, you will have two slack variables correspondingly. And this will brings you some ambiguity issues that, okay, your agent needs to infer which state is actually it is. But with the exponential slack variable, it's better, since it's a diffeomorphic mapping and it never goes to zero. The only problem is like the tangent space is morphed with respect to original one, such that if you think about a unit vector here, it will be not unique vector along the s direction. And then to tackle this problem, we actually introduce a soft corner problem, a tangent space, soft corner slack variable that really tries to deform the tangent vector as minimum as possible, such that if you are far away from the constraints, you will be aligned with our original action space or velocity space. But if you want to look into this part, you can probably look into our recent paper on the on the Accra paper that we have is here. It's basically we have discussed the slack variables more in detail.
Okay, thanks. Do we have any other questions from the audience?
I have a question. I have several questions actually.
Okay, there's also one in the chat, but
Okay, maybe you can first answer the
Okay.
question
so
from the chat.
does the question ask, does the constraint manifold necessary to need does the state to calculate the project the actions on the time space? If yes, what exactly? Unobservable part of the system state. Yes, so we actually really need to observe the state. So if you see from the controlling paradigm, that we need to actually observe not only the state but also the velocity. And in this case, you can assume that the velocity is this one. You can use a filtering, or you can do some state estimation common filter to estimate, or you probably can also assume that this goes to 0. It's actually also working well in practice, but theoretically there will be some some issues. And if yes, what exception can be made to apply the method on observed part of the system state? Well, actually, that would be a bit problem if you don't you cannot observe the system state, right? Like you cannot really say, okay, this thing is safety critical states or not, since you don't know how the state goes. But I do believe you can still apply some state estimation approach or using filtering to have some rough estimation. For example, in this kind of scenario, we actually tested both observing the state of the blue robot, or we use compute the state based on the robot, or we completely assume the state to be 0. Actually, all of them works decently well, but definitely if you know the full state of the robot, it's works the best. And for the human robot scenarios, actually we don't have the access of the human's velocity, like the joint velocity, and that in that case we actually assume the velocity goes to 0. But if you don't observe the states, that will be problematic.
Okay, thanks. And what's the difference comparing outcome with formal methods? And also, formal methods can also be used for harder constraints. You know,
So you are referring to these
formal methods
modifications
yes,
that we have?
Yeah.
Basically,
the difference is comparing outcome with formal such as reachability in analysis.
well, that would be actually, I think this is actually one advantage. Like, no, we actually compared not with the reachability analysis approach, but with some like a safe exploration approach, like what's the name? This safety layer. So one big advantage is that in most of the safety layer or this kind of approach, you either need to have a backup policy that ensures you to be safe, or you need to formulate into a constraint optimization problem such that you find the constraint actions while the constraint is unsatisfied. But in our case, actually, we don't need to modify solve another optimization problem, since all of the actions sampled in the space ensures the safety. So I guess that would be some sort of advantage that, and also it can incorporate, since we construct the action space, so it can incorporate into any safe reinforcement learning approach. And you basically just sampling differently at the action space. And for the reachability, and also some approach, like for example, this control barrier functions would also be a very popular one, that I guess we can directly incorporate this formulation of the control barrier functions into as a constraint, but we don't need to solve another optimization problem. So we can directly use the control barrier functions as constraints, but construct the constraint manifold to do explorations.
Okay, thanks. And what's the challenges when we use outcome for robotics?
So one of the challenges actually is that if you have, so I think in the human-robot interaction scenario, we actually have a pretty high-dimensional input space, like 70 or 84 dimensions. I don't remember exactly. Then when you're computing the Jacobian, you actually need to compute the Jacobian in these dimensions, which is done by neural network, so it's fine. But you also need to compute the pseudo-inverse and the non-space, which this one, I mean, computing the pseudo-inverse, you basically use SVD, which just scales up cubically with the dimensions. That will be a bit computation heavy. And regarding the rest of them would be, yeah, maybe the computing the null space, because in general, or the tangent space of the constraints, that the basis you don't have a unique solutions of the tangent space. So that's why in general, it will be, we actually struggled a lot to really find, okay, what would be the best formulation of the tangent space. But right now we are have some really good results with our current work. And I guess we will also submit to a journal paper very soon. And then maybe if you are interested in this part or have curiosity on this part, maybe stay tuned with our new approach that ensures a smooth variant, and also consistent tangent space. For example, if you see from this, where is this circle experiments? Wait a second. Oops, I didn't really find it.
I think one of the most important things is the symmetry real, such as the stimulation to the real world robots.
Yes. So if you see from, let me finish the questions I have for that. So for example, in this kind of tangent space, if you see that on the upper part, the tangent space is going on this direction, and on the lower part, so there will be some disconnections. Even it will not be so much problematic, but we actually really want a very smooth varying null space. So basically, I mean, from the human perspective, it's very easy to construct, but mathematically or for high dimensional case, this thing is actually another challenge that we have trying to get rid of. Okay, sorry for the interrupt. This is you can continue with the questions.
Okay, there's a question from the audience. You can see chat.
Okay, can you provide the hard safety guarantees where constraint is approximated? Will the constraints was the constraints manifold? So yes, this is actually one of the questions that we always have. Like when your constraints manifold is approximated, definitely you cannot have strong safety guarantees. But what we have observed is that if you have an approximated one, you probably need a higher or slightly higher margins of the safety region, such that, for example, in this SDF mode, we actually define the margin to be 3 or 5 centimeters. I don't remember completely, but this margin to avoid the collisions is actually sufficient in our scenarios that we don't really have any collisions during the training or during the real world deployment. And when the constraints are approximated using a critic network, I'm not very sure if I understand what does it mean with a critic network. Yeah, I'm not very sure if I understand this critic network properly, but I guess if the general answer would be approximated, you cannot assure the safety guarantees, definitely. But you can have higher margins that will work decently. And Hossein has another question about the fact that projecting the action to the tangent space externally changes the distribution of the hypothesis training. Have you tried to? Does it make sense to make the agent aware such changes by outcome? So this is actually what I was trying to deliver here, because we are trying to construct a basis that would be consistent and smooth, such that if you are doing the projections, yes, you are moving your action space to a completely different dimensions. But in your case, the action space will always be consistent. Even the basis will be changed, but it will be like whenever you face the same state, you will have same basis, such that you don't have any ambiguity or on this part. And this is actually the problem that we are hardly working on.
Okay, then I can comment here is that so far you have considered constant basis functions actually. So the way if the task is going to change or if the constraints are evolving and being changed, so the manifolds are also being changed, and that's what I thought that maybe augmenting some sort of these contraction and these propagation terms which we are seeing here and making the agent to be aware of such external changes might help even, for example, for continual or transfer learning something.
Yeah, definitely. I totally agree. Like this is also like a pretty, I would say it's a reinforcement learning problem instead of the safety problem, right? So basically, if you have a non-stationary environment, that you will have probably the state visitation or state distribution will be completely different based on the dynamics of the system. Yeah, that the reinforcement learning can it can have problems, but also since we are ensuring the action or this contraction term ensures your safe, the policy to be safe, and you probably definitely need more like doing transfer learning or doing continual learning would help to resolve the big problems. But for example, in the human-robot interaction scenarios that we have here is actually we are recording some human behavior completely blindly without any like a robot involved. So the human is actually doing random work with a table like for 10 minutes, if I'm not wrong. And then we just use this data set to train the things and deploy with some structured or at least some specific task. And this also explains a bit like well that if you have a dynamical constraints, then probably your network or your agents would try to learn something that will be invariant, like have some sort of invariance with respect to the environment dynamics. Since, for example, the human is always stands up and reset to the position.
Yeah, that makes sense. Thank you.
Okay, thanks. For just great talk.
Okay, thank you very much. Thanks for such an interactive discussion.
Okay, so
Yeah.
I think
Thanks
that's all.
everyone for joining, and hope to see you in the next talk.
Okay, bye.
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 Thank you. Bye.